Good afternoon, everyone, and welcome you all for today's class. And today we are going to start a new topic, that is solar energy and its applications. Before starting to introduction of solar energy, I want to focus on the very core topic of the collector efficiency factor, because in solar energy we have to cover so many topics, but starting from the solar thermal, because solar energy can be converted into electricity, or in terms of the heat energy, by two ways: photothermal and photovoltaic. So here, first we are going to discuss about photothermal, part of the energy harvesting using a collector. So one of the most important collector is a flat plate solar collector, universally applicable everywhere all over the world. It is a most convenient way of collecting solar energy in terms of heat energy for various applications. So one of the most important thing that is required for the design of the flat plate solar collector, or any collector, whether it is a concentrating collector, paraboloid collector, disk collector, all collectors, there are there are some common things. For example, when designing collector, we have to focus over collector efficiency factor, collector heat removal factor, collector overall heat loss coefficient, collector transmissivity. For example, for applicable, that is applicable in flat plate solar collector. What is transmissivity? So one of the most important parameter of the collector design or collector performance evaluation is collector efficiency factor and collector heat removal factor. These are two major parameters which defines collector performance index. So first we will define collector efficiency factor, and then we derive collector heat removal factor. So what is a collector efficiency factor? This is a very complex derivation. I will derive it later. But I will define here what is a collector efficiency factor. So let us first define what is a collector efficiency factor. Irresponsible how collectors is efficient in transforming energy absorbed by the collector observer plate to the collector tubes through which fluid is flowing. So how much collector absorber plate is efficient in absorbing energy and transforming it to the collector tubes. So let us make a design, and that will be helpful in defining collector efficiency factor. So see here, this is we have taken this is absorber plate having thickness del P. This is absorber plate inside the collector. These are two tubes below the absorber plate. These are because there are two arrangements. Either collector, this is fin type arrangement. Either tubes are above the absorber plate or tubes are below the absorber. We are taking two tubes, and width of these are tubes are along the width, because along the length, these are length of the, there will be length of the tubes. So this is let W is L2. L2 is a width of the tube, width of the absorber plate, absorber plate, and L1 is a length of the absorber plate. So it is obvious that L1 into L2 becomes area of the absorber plate. This length, this is a width along the, and between two tubes, that width is W. Between two tubes, it is a pitch of the tubes, because this is a regular interval. At this regular interval, tubes are arranged. So pitch of the tube, we can define W equal to L2 by N. Here N is number of tubes. N is number of tubes. So this is a schematic that will help, and this is temperature distribution. This is temperature TP, TPO, and here temperature TP. And this temperature is varying between two tubes. Here temperature will be maximum at center point, temperature is maximum, and as we move, because through conduction heat is going to tubes. So here heat is going to tubes like this. From here also, because from both sides heat is conducted from observer plate to the tubes. So this is arrangement to explain collector efficiency factor. And here are two tubes. Internal diameter of the tube is di and outer diameter of the tube is do. Do is outer diameter and di is internal diameter. And let's define what is a collector efficiency factor. Collector efficiency factor derivation is little bit very complex, so it will take more time. So first I will define and then we define collector heat removal factor. It is very important. That is little bit easier and manageable to derive it. So I want to define collector efficiency factor. Here it is 1 by n dqu by dy, that is equal to f dash w s minus ul tf minus ta. This is a collector efficiency factor. F dash, which you can define useful heat gain. dqu useful heat gain per tube. N is number of tube per unit width, because dy is along the length of the tube. So useful heat gain dqu is useful heat gain per unit length and per tube equal to f dash w. W is pitch, s is in effective intensity of radiation reaching to the observer plate, ul is overall heat loss coefficient, tf is fluid temperature flowing through the tube, and ta is ambient temperature beyond the collector, ambient temperature surrounding temperature. So here you can define f dash. F dash is defined by 1 upon w ul in bracket 1 upon ul w minus d naught into pi and plus d naught bracket plus del a upon ka d naught and plus 1 upon pi dihf bracket close. So this is a collector efficiency factor. This term is a collector efficiency factor. By defining this collector efficiency factor, useful heat gain per unit width, per unit length of tube and per tube is become very simple. F dash. By introducing F dash, this equation becomes very simple. That's why this equation is defined to manage the equation. And ul is a overall heat loss coefficient, s is a effective intensity that is reaching over the collector tube, that is a s, and it is absorbed by the observer plate, and tf is a fluid temperature that is flowing through this tube, and ta is a ambient temperature, that is a. So you can define here by using this equation, we can define collector efficiency factor. It is defined by ratio of useful heat gain per unit width per tube by useful heat gain when collector plate temperature become collector fluid temperature flowing through the tube. Once again, this factor can be defined as f dash, because here you can write f dash equal to 1 upon n dqu by dy upon upon w s minus ul tf minus ta. So this is a, in this equation you can define, it is ratio of useful heat gain per unit length per tube by the useful heat gain when collector plate temperature equal to fluid temperature of the fluid flowing through tube. When collector plate temperature become, that Tp become Tf at this, because this is a this will be always less than 1, because this Tp can never reach Tf, means collector plate temperature can never be equal to T or fluid temperature of the tube. That's why this ratio is always less than 1. So this is effectiveness by which we can define collector performance. So this is a collector efficiency factor F dash. This is a way we can define collector efficiency factor without deriving. In short manner, by effective way, we can define collector efficiency factor, most important factor, because this factor again we are going to use in defining collector heat removal factor. Collector heat removal factor. So next we define collector heat removal factor. Collector heat removal factor. The heat removal factor. Collector heat removal factor, that is defined by F. So let us make a schematic for this one. Let us make one tube. Take a one tube. This is a one tube. Out of some n number of tube, we are taking only for one tube, because when we multiply one tube by n, useful heat gain of the one tube multiplied by n, then we can get useful heat gain for all tubes, for whole collector. That's why we are defining for, and length of this tube is L1. Width was taken L2. Already we have defined. Let us take here one element, a small element. This is a small element here of dy thickness, of dy length, and at this point at here y, because we have taken along the length we have taken element y, so at this point y equal to 0, and here distance is y, and here distance is L1, y equal to L1. Temperature become TFO. At y equal to 0, temperature is TFI. TFI. At this point at y, temperature is TF. When it move dy distance, temperature become TF plus dTF. So we apply first law of energy balance, applying first law of energy balance, first law of energy balance equation, applying first law energy balance equation, and we see here graph temperature variation will be like this. This is a temperature variation curve along the tube, will be like this. This is a temperature variation, because at inlet temperature is minimum, at outlet when fluid will go out from the tube, it with temperature is TFO. Maximum temperature will be measured when fluid will come out from the tube. At entry at y equal to 0, fluid temperature is TFI, that is a TFI. This is a variation of temperature, and so minimizing it. Writing energy balance equation for this, because enthalpy will change of this fluid element, and that enthalpy change in fluid element will be equal to useful heat gain by this fluid at dy distance. How much useful heat gain by this element of the fluid will be equal to change of enthalpy of this fluid. So that is this equation we can write m dash is mass flow m dash by n, and Cp dTf, because temperature difference that is occurring between y equal to at y and y equal to y plus dy, because here distance become at this point y and y plus dy. So at dy distance temperature change is Tf to Tf plus dTf, so temperature difference is dTf. So that is a change of heat energy, that is equal to useful heat gain by this element over this length, that is equal to that is equal to 1 upon n dQu, that is equal to, from earlier equation that we have defined in defining collector efficiency factor, from that equation we can see it is equal to Wf dash S minus UL Tf minus Ta multiplied by dy, because we are taking useful heat gain by this element in dy distance, so we have to multiply, because we have taken here 1 by n dQu, and dy we have taken here, so multiplying dy here you get same equation that we have defined for collector efficiency factor. So now balance using this equation for derivation, so dTf equal to W F dash N upon M dash Cp. What is M dash? M dash is a mass flow rate, flow of mass through the whole of the collector through n number of tubes. M dash is a mass flow rate. M dash equal to rate of mass flow rate. Mass flow rate from collector, and m dash by n equal to mass flow rate through one tube. Mass flow rate through one tube in kg per second. That is a kg per second. Kg per second. So dTf equal to Wf dash n upon mcp, and in bracket you will see s minus ul tf minus ta dy. So taking out ul, taking out common of ul, so that will be equal to w f dash n ul upon m dash m dot cp. In bracket you will get s upon ul minus tf minus ta dy. So balancing this equation again, and we get dtf. This is equation number, you can say this is equation number dtf equal to equation number 1. This is equation number 1. So now erasing this one, this part not needed for me. This again. So dtf upon s upon taking out ta, because when you open the bracket, ta become positive and tf become negative. So this equation you can write s upon ul plus ta minus tf. This way equal to equation will become wf dash n ul upon m dot cp and dy. This is equation. Again, this is equation number 1 because only we have done just simplifying it. So earlier we have shown in collector efficiency factor defining, because length of the collector tube is L1 and width of collector tube was L2. So L2 into N. We have defined L2 by N equal to W. So W into N can be written as L2, width of the collector. So here we can write, instead of writing two letters, we can write only L2. So this is equal to W, this become F dash L2 into UL upon M dot CP into dy. This is equation number 1 again, because there is no change. And now this is integratable. Now integrate this equation for indefinite integral. So integrating this equation for indefinite integral, we get, now integrate this equation. So minus, because here you can see minus and left side these are constants, and ul, you know, the L is not any number, it is only suffix. Ul means overall heat loss coefficient. Overall heat loss coefficient. Integrating this equation, ln s upon ul plus ta minus tf equal to f dash l2 ul upon m dot cp into dy into y and into y plus c. This is equation number 2, because this is a different equation. So how we can get this constant? By applying boundary conditions. By applying boundary condition, we can get constant here at y equal to 0, tf equal to tfi. Here you can see at y equal to 0, tf equal to tfi. Temperature of the fluid inside tube is varying throughout the length. At y equal to 0, inlet temperature. tfi is fluid inlet temperature. So putting here value at y equal to 0, this equation you find ln s upon ul plus ta minus tfi equal to c. This will become 0. So now we get constant c, and putting this constant here in equation number 2, we will get another equation. So putting this constant in equation number 2 and balancing, after putting this constant in equation number 2 and balancing this equation, we get equation in this form. Ln. Now writing, putting this equation, C in equation number 2 and balancing this equation. So we get ln S upon UL plus TA minus TFI upon S upon UL plus TA minus TF. This is equation. After putting value of C in this equation number 2 and taking this C value left side, you get this equation equal to F dash L2 UL upon M dot Cp into Y. This is equation number 3. This is equation number 3, but again we need to balance it. Now erasing this part. For creating space, now erasing it. So taking antilog of this equation, S upon UL plus TA minus TFI upon S upon UL plus TA and minus TF equal to exponential and F dash L2 UL upon M dot Cp into Y. This is equation, and you can say this is equation number 3. If we reverse this value, just for the managing this equation, if we reverse this, exponential term only become negative. Reversing this equation just to manipulate this equation. Now reversing this equation, S upon UL plus TA minus TF upon S upon UL plus TA minus TFI equal to exponential minus, because now reversing this become minus F dash L2 UL upon M dot Cp into Y. Now putting another condition, this is equation number, you can say again it is 3, because only thing that we have done is just reverse 6, equation number will not change. Now putting another boundary conditions at y equal to L1, TF now become TFO, fluid outlet temperature from the tube. So putting y equal to L1, so this equation become S upon UL plus TA minus TFO upon S upon UL plus TA minus TFI equal to exponential minus F dash L2 UL into L1 upon M dot Cp, because we have put a y equal to, now putting y equal to L1, TF become TFO. So this equation, this is again equation number, now this equation become, because now this equation is different from equation number 3, because we have now applied boundary condition at y equal to L1, TF become TFO, here temperature is TFI temperature, and what temperature. So only thing that we have to require that this we have to, because we know that L1 into L2 is a collector absorber plate area. You can replace L1 into L2 equal AP, collector absorber plate area. L1 is the length of the tube, length of the absorber plate, because length of the tube is equal to length of the absorber plate, approximately both are same, and L2 is a width of the observer tube. So L1 into L2 you can write AP, L1 into L2 write AP. So now this equation become S upon UL plus TA minus TFO upon S upon UL plus TA minus TFI equal to exponential minus F dash UL into AP. L1 into L2 become AP, area of the observer plate, M dot Cp. Cp is a specific heat of the material, of the observer plate, and m dash is a mass flow rate. Mass flow rate. Cp is not a material of the specific heat of the observer, but Cp is a specific heat of the fluid flowing through the tube. Cp is a specific heat of the fluid flowing through the tube. M dash is a mass of the flow rate of the fluid. Now only thing that we have to require for getting required equation, subtract both side by 1. Subtracting both side of the equation by 1. So this become 1 minus S upon UL plus TA minus TFO upon S upon UL plus TA minus TFI equal to 1 minus exponential minus f dash ul ap upon m dash cp. This equation. So now if we subtract, take this here and subtracting this one, you will get equation. But now simplifying this one, TFO only get TFO minus TFI upon S upon UL plus TA minus TFI equal to 1 minus exponential minus f dash ul ap upon m dot cp. M dot cp means m dot is mass flow rate in kg per second. So now almost equation is now clear. So now replacing this side. Now useful heat gain for whole of the collector. We can define useful heat gain QU for whole of the collector equal to m dot Cp into TFO minus TFI. This equation now equation number 5. And taking TFO minus TFI from equation number 5, you can take TFO minus TFI from equation number 5 and putting here in this equation number 6. If it is useful heat gain for the whole of the collector, m dot is a mass flow rate, Cp is a specific heat of the fluid, and TFO is a fluid outlet temperature, TFI is a fluid inlet temperature from the tube, from all tubes. So this is a very simple equation. Putting this value TFO minus TFI from equation number 5 here. So QU become m dot Cp, and this will become S upon UL plus TA minus TFI and in bracket 1 minus exponential minus f dash UL AP upon m dot CP bracket close and full bracket close. Only thing just for take out UL outside. Take out UL outside. So m dot CP upon UL, an equation you will find here S minus UL TFI minus TA bracket close and 1 minus exponential minus f dash UL AP upon m dot C. This is equation. Just only thing that we have to do just multiplying C by AP nominator and denominator. In this equation, multiply by AP nominator and denominator. So it become, this equation will become now here writing that is equal to m dot Cp into AP. We are multiplying nominator and UL into AP denominator, and in bracket S minus UL TFI minus TA 1 minus exponential minus f dash UL AP upon m dot Cp bracket close. So this is a final equation. Here we have to define what is a collector efficiency factor. So taking by another color, this part we take out, and this part we take out, and this whole part is converted into a constant that is known as a collector heat removal factor Fr. Collector heat removal factor Fr. So now writing this final equation in this form. So now QU become Fr into AP. This equation become very simple. S minus UL TFI minus TA. This is a very simple equation number 7. By defining heat removal factor, whole of the equation become very easy. So now here we can define what is a collector. First we define what is a collector, what constant Fr stand. So Fr equal to m dot Cp upon ULAP in bracket 1 minus exponential minus sign f dash ULAP upon m dot Cp. So now to remember is very easy because you see here m dot Cp, m dot Cp, ULAP, ULAP. Only thing that multiplied by here collector efficiency factor. So remembering this collector heat removal factor equation is easier compared to collector efficiency factor. So I think this is final derivation, and finally we have defined no collector heat removal factor. But what is the physical significance of collector heat removal factor? By using this equation you can define collector heat removal factor very easily. So now defining collector heat removal factor, Fr equal to QU, useful heat gain, upon AP, area of the collector absorber plate, S minus UL, TFI minus TA. From equation it becomes very easy to define collector heat removal factor. It is a ratio of useful heat gain by the collector to the ratio useful heat gain by the collector when a collector plate temperature equal to fluid inlet temperature of the tube. Once again, what is a collector heat removal factor? It is a ratio of useful heat gain QU by the collector to the useful heat gain by the collector when collector absorber plate temperature TP become TFI, that is this temperature, because here you see TP become TFI, fluid inlet temperature of the collector tube. This is very simple. It is ratio of useful heat gain by the collector to the useful heat gain by the collector when collector plate temperature equal to TFI, means fluid inlet temperature of the collector tube. This is a physical significance of the collector heat removal factor. Collector heat removal factor Fr, now you see related with the collector. Higher the collector efficiency factor, higher the collector heat removal factor, higher will be the performance of the flat plate solar collector, any collector. Everywhere, whether it is a concentrating collector, parabolic collector, everywhere these two factors are cardinal for defining collector performance. Any kind of collector, these two, on the basis of these two parameters, we judge how much collector is efficient. And we always try research, innovation, design, everything focused over how to increase collector heat removal factor and how to increase collector efficiency factor. Thank you very much for watching today's lecture. Please like and subscribe and share and make your comment so that I can motivate myself to produce these videos and in-depth videos and discuss. Thank you very much and have a nice day.